Magically, it happens, right?
Good morning. And welcome.
Got 1 minute.
Welcome to the session. Yeah, well, we're starting early, good in time, just with the intros as people still coming in. And hopefully online, the people will hear me through which device? I'm asking the organizers, is there a microphone for the online people that they will hear me?
Yeah.
Is it basically in here or also when we have questions later? That's all there.
That's this for the room, and they can also get you.
Wonderful.
So they could hear you as well.
So hopefully you can hear me online.
Yeah.
I'll just open here the chat. Sound is good, fantastic. So thank you very much for the
Good to hear.
Slides are gone. There's no projection right now.
now the projection is on.
Did you consider this one with a because it was something about you. Find.
Still in the Zoom.
Yes. I think I must get a technician.
Yeah. I'll continue a little bit. I mean, you kind of know hopefully what this session is about since you're here. In particular, I could just introduce also the objectives of why we're here. It's really what we want to do is discuss the advances in using semantic artifacts, ontologies for more standardized documentation and data representation in chemicals and materials. There's a number of activities obviously going on in this. This should be focused across these two areas, first of all, and to review the approaches and recommendations for the development and harmonization of domain ontologies as a common resource. So it's sprung also from the experience from a number of projects. You say, okay, it would be great to have all the terms well defined, to have some resource like an ontology that I can then actually use in a project rather than starting from scratch every time. And this is basically where we are at the moment, where we have a lot of need, but not a lot of resource, or the resource is a bit scattered, or the resources are used or developed in different frameworks and maybe not sufficiently semantically fair as well. There are obviously other groups that look after this type of generic need, and I don't want to sort of tread on their toes, but really look at it here from the needs of the domain and domains of chemicals and materials. We're still in a room here waiting for the projection to work, which somehow seems to have given up. We will have a number of speakers, and I'm just going to introduce also with a few slides my perspective here, or some perspective from this work, but then I would really need either everyone in the room also to go into the session.
We want to mention the shared document, the notes. Do you want people to put it there?
That's also a good point. Yeah. So there is the collaborative notes. So if you please join that one, you can also enter your attendance details there. And yeah, okay, it's already shared. Thank you in the chat. Please go on that when you in the session. So also for the people here.
I'm waiting. It's something resetting.
Resetting.
Yes, I have to do that. Still waiting.
It's suspicious. have a coffee.
Yeah.
Yeah. So can we just, since in a talking mode, have just go quickly around the speakers while we're waiting. Emanuela, are you there? Can you speak?
Yes,
Especially
I'm here. I
online.
can speak.
Okay, Emanuela, and yeah, please just say what you're going to introduce. What your talk is about.
Yes, I'm well, I'm a nuclear engineer, but currently I am one of the MMO ontology developers within the EMMC. That's my job here.
Okay, thank you. And then James Hester.
Yes, hello. Can you hear me?
Great, thank you. Yes.
Yes, good. I'm going to be giving a little update on what we've been doing to bring crystallography into MO. Yes, that's about it.
Hey, that's James Hester from ANSO and joining us from Australia. Thank you.
Yes.
And then Patrick Lambrix is here. If you just want to say words as well.
We'll be talking about finding semantic and integrated aspects.
Thank you, Patrick from Linköping. Then we have David Albert from Johns Hopkins.
Yep, I'm here, and I'm going to talk a little bit about material-specific RDA, the MARTA, the Materials Research Data Alliance, which started in the US, now has lots of international representation, and some of the working groups there that relate to semantics that could link to ontological work.
Thank you. Then Una Manix, please.
Yeah, I'm going to be talking about a glossary that we're developing with the electron microscopy community. And yeah.
And you're representing Helmholtz.
Helmholtz metadata collaboration.
Thank you. And Stuart.
Yes, Stuart Chalk. I'm the technical editor of the IUCAT Gold Book, and I'll be talking about that in this session, giving everybody an update on where we are.
Thank you, Stuart. And then we have online Philip Vermaat.
Yeah, hi.
Right.
I'm representing NFTI for Chem, and I'll be giving an update on our terminology service work.
Thank you. And then we have Kwang Lee.
Hi, my name is Kwang Lee. So I'm talking about some Korean effort to build a data structure for material science.
Thank you. And then we have Scott McClellan. So Jane Greenberg is also here, so if you both want to.
I'm Scott McClellan. I'm working with the Metadata Research Center at Drexel University, and I'm going to be talking about term overlapping and map portal ontologies.
And then if once we get through the presentations, maybe, and if you can maybe think about that as well. I mean, one idea was that, do we have a group or a desire here to start or apply for a working group in the RDA, about this field of how we can actually move this forward together. Because there are, I mean, we did what I will show also. I guess the online people at least can see it. I will, and if you want to join also online, then maybe that's another way of moving forward. Is that we analyzed the field in a project called OntoCommons and also OntoTrans. These are two European projects. We looked at about 50 ontologies, which we gathered from surveys as well as from the map portal and the OntoCommons industry portal. And then we looked at them, first of all, they are either sort of mid-level, domain level or application level ontologies, and they also belong to or are in different upper level ontologies, including the SIO, MO, BFO, SUMO, and also ontologies, domain ontologies and applications that are not in a in a top level ontology. And then we also did, we made a glossary or used a glossary and extended the glossary of terms in material science. So from the textbook by Callister, Modern Material Science and Engineering, we added a number of terms from the modeling and characterization field, and also from some applications and demonstrators, which we have in the OntoComs projects, coming up with 800 terms, which we then grouped into different fields or subdomains of materials. So some, for example, terms like alloy or polymer describe materials classes, others describe structures or properties, behaviors like tribology, technologies like modeling, characterization, theories, and devices. So we came up with these 7 domain areas, and then we looked at, so each of these domain areas had about sort of 100 to 150 terms. And then we looked at what is the coverage of terms, right? I mean, because you want to say, okay, I need, hardness, I need alloy, and so on in an application. So what's the coverage of ontologies in there? And so a lot of the coverage was in the sort of few percent range. In some cases, it was up to 35% maximum, right? So on the whole, but then that would be maybe in the properties areas, but not in the materials classes area. So you wouldn't find typically ontologies that would fulfill the needs of an application just in terms of the coverage of terms. So that was one finding. The other thing is we then looked at what are the most frequent terms to come up with what are the terms for bridging between different ontologies, kind of mapping or crosswalks. But we use a term, something what we call a bridge concept, which is more of a richly annotated term. And so there we found that sort of the top ones, most frequent ones across different ontologies are obviously material, but also then, because we included chemistry, also atom, then structure, component, property, and phase. And then we also did a bridge concept for material component as one example of showing how you can connect MO ontologies and then HEBI from the chemistry side, eNanomapper, materials mine. So a number of ontologies around this common concept. So we're also extending this as one way of applying, how you can actually make existing resources more connected and more interconnected, more usable. But okay, that's just one thing. And obviously, what we want to hear from more people here about what they've done. Just want to acknowledge here the work by my colleagues from Goldberg Consulting, Anna de Bas and Daniele Ciotti, and Ilaria Paponetti and Emanuele Ghidini, who's also online from University of Bologna, and the OntoComs project and the OntoTrans project that received European Union funding for the Horizon 2020 program. And now I just want to hand over to Emanuele to continue with his talk.
Okay, thanks, Gerard. Since Gerard already presented the OntoCommons approach, I decided to propose a more focused presentation on the EMMO ontology so that you can really understand how crazy we are in our ambition to create an ontology for material sciences as the EMMC. Next one, please. So you all know that materials and product development are sponsored in multiple expertise in multiple subdomains. We have multiple information and data resources. We have several languages because each domain has its own language, its own way to handle data. There is a lack of a common presentation system for this knowledge. So next one, please. What we decided to do with the MMC is to try to rely on ontologies in order to provide a common ground for the knowledge representation. You know that ontologies are not a different way to set up a database. They are about describing knowledge. So capture material science knowledge, and they can be used to semantically document existing or new data and to integrate them in a shared knowledge system. And we leave in our effort data processing and mathematics to separate implementation, but the ontologies should pave the way for these activities. So if you want to create a common knowledge framework, you have to rely on another ontology that will create you a common framework of base language and rules to represent applied science knowledge. So in particular, if you want to deal with if you want to use a scientific view of the world, you need to deal with some absoluteness. So there is a universe, there are some natural laws, patterns that have been recognized by physics. But there is also subjectivity of observation, because, for example, measurement can be different between two different experimentalists, or you can have models providing you different results. But there are also accepted scientific laws that needs to be in some way included in this ontology. Next one, please. So what we want to capture in an ontology is to capture and communicate the observation, so the data that can be inferred from reality and how they can be expressed and communicated to other agents. We want to clearly represent physical entities. We want to clearly scientifically understand space-time relation between things. We need to have hierarchical connection between the entities that form a material entity. We want to connect entities with models or physical laws. We know that there are absolute things, so the universe and the elementary particles, and we want to deal with quantum system. So next one. So if we succeed in creating an ontology like that, we will then be able to facilitate the translation of material representation into a physics-mathematical machine processable problem. So an ontology can be a way to set up a problem that will be dealt by other more science-specific tools. We can set up a regular set of user cases, facilitate gathering of data, or regularly represent different methods that can be applied to predict properties of behavior of entities. So next one, please. So what we decided in 2018 with the EMMC is that in the ontology world, there was no such an ontology that was able to capture what we needed as applied scientists. So we decided to build the EMMO ontology, which is elementary because it's fundamental from sees things as made of elementary particles, for example. Put the perspectives that tries to capture the subjectivity of the observation, measurement, modeling, theories, and so on. And it is based on causality, mereology, and semiotics. Next one, please. So as you can see here, the ambition of the MMO is to describe things as a composition of elementary particles. So we started creating a logical theory that tries to infer from the rules of Feynman diagrams the rules between the connection of this elementary entity that we call the quantum. So this is a really a bottom to top construction of a theory of things. Next one, please. And but also we want to retain this subjectivity. So while we know exactly what things are, we are not like in the times of Aristotle, in which the science of being was something guess. Well, we know that things are made of elementary particles, but also we have some sort of subjectivity that we have to retain. And here we are the perspective. So built on this, objective ontological part on mere causality, we create a set of perspectives that gives you the possibility to look at things in an obliquous way. Next one, please. Next, please. Okay, and also it's really important to represent in the ontology also the data, because the data are the way in which we communicate each other the content of our observation. So we also built a strong data representation based on the work, for example, of Luciano Floridi on information theory. Next one, please. In fact, here you can see how the MMO works. The MMO is really distinguished between the physical entities that you want to represent on the left, so using this mere causality representation. Then it helps you to define the data that you're dealing with in a syntactic way on the far right, you see. But also it can give you an insight about how these data are connected to the physical entities. In this way, we can represent in this ontology the information being data with meaning, and we can do that thanks to the semantic. So as you can see here, our material sample is connected to a zip file, for example, but through the work of an experimentalist. This is everything. This is something that you can capture in this ontology. Next one, please. Next, please. The next slide. Next. Okay. This has been applied, but probably James will tell you something more about that. Also in several fields, in particular in the crystallography field. Yes.
It's we just need to pause here because we have some work going on in the room to try and pick a projector.
Okay.
With people coming in with a ladder. We are experiencing, well, they might be able to see it on the There we go. You can actually see it. You won't be able to see it online. And we experience it in full physical.
What happens? You're in person, right?
It's a perspective session.
This is totally in line with my presentation because this is the Wittgenstein ladder. So that you can use to climb and to reach something, and then you can throw away. That's exactly in line with our approach.
Yeah.
Thanks for this contribution.
Just keep going, yeah.
Should I continue with the presentation or wait?
I mean, you can continue, but we can entertain us. Yes. Or we can have a little discussion about crystallography, but
okay. I think you took to literally my bottom to top approach.
We are.
Very difficult, very difficult.
Yes, we can only say that we are so sorry about this. We have to find a solution if you can't get the projector right.
We can continue the talk.
It's a degree and something is happening.
Takes a while, an hour. Maybe we can ask in the meantime.
Maybe if you have any questions, we can maybe anticipate.
We can now see your presentation, Emanuele, for the first time.
What? For the first time? So you didn't see anything from the beginning?
Only the people that were joined in the online meeting, but no,
Not in person, anyway.
not on the screen, not in the room. Unfortunately, no.
First class trainer.
I'll give you another chance with the perspectives, maybe just briefly start from there.
Yes. So the perspectives are okay. As I told you, we rely on strong reductionism. So in order to say what things are actually or objectively, but also we have the possibility to represent things in different ways. So going in the direction of in particular perspective in which things can be seen, you know, as a multigranular entity in the case of reductionism, as data in the case of data perspectives, as you know, semiotics entities, so signs and object, holistic approach, so in which we have the whole and the parts, and so on. So this is the way in which we combine objectivity and subjectivity. Also, data are really important for you know, for science. So we also need to represent the syntax, the syntactic part of the data, and that are connected to the semantics and physical entities in like that. So this slide is really important because it tells you how the EMMO works. So on the far left, you have the physical entities, so the objective part of the ontology, in which you say what things are. On the far right, you have the syntactic part in which you represent syntactically how your data are, I would say, serialized or syntactically represented. And you have the semantic part in which you connect, for example, a model to a physical entity or a data set to a physical entity, always and always keeping track of the semiotic process. So keeping track of who is the authority, in this case, in the example of an experimentalist, that see a connection between a data, a CIF file, for example, and the material sample to which this CIF file is assigned, so it is a model. Next one, please. We apply this to the crystallography ontology, and James will tell you probably something more. And as you can see, the value, so which is actually the data that you store in your file, can be considered as something belonging to a syntactic entity, a semantic entity, and a data type. And at the same time, is related to a particular word material. So this value is about something. So in this way, we capture all these four, I would say, four aspects. Thanks to our reductionistic approach, we can represent also material in a very general way. So we are able to move from the elementary particle to the macroscopic material. You can see here our approach to a material ontology, in which we move from the left, in which we have the particulate matter, so matter that are nuclear or subnuclear, also up to the molecular entity, and the material that is seen as mesoscopic or continuum. And we build our material ontology upon this concept of material. Next one, please. Doing so, we are able to represent things in a multigranular way. So if you're interested in a particular level of granularity, you can focus on that particular level. But if you want to go up and down, it is possible you have the tool in the MMO to dig down into the constituents of a particular entity, or to have a look at the higher level entities to which your entity is part. Next one. Also, we are working on other less material-oriented modules, like, for example, the manufacturing module, in which we represent, using the holistic branch of the MMO, the manufacturing activities. We have found that the DIN 8580 norm is really very interesting and well done in order to represent manufacturing. So we are starting to build this type of ontology module, so the manufacturing ontology module, based on this knowledge. So that concludes my my overview of the EMMO the ontology of the EMMC. Thanks.
Thank you. Thank you, Mike. So in the interest of time, we will carry your stuff on. I'm not sure where we are in time, but we'll hand over to James, Hester, and please go ahead, James. Yeah, if you can keep it to about 5 minutes, that would be great.
Yes, well, seeing as how Manuela has covered MO, I won't have to talk about that, so that's good. So we might as well go straight on to the next slide. I know most of you have probably never heard of me before, so just a quick introduction so you've got an idea of where I come from. I work as an instrument scientist at a large-scale facility here in Australia, and I've been doing that for many decades. So I see data produced and I follow it through its life cycle essentially, and I see many different scientists come through the instrument. And so I have that particular perspective of the practical working scientist, I guess. My other hat that's relevant here is that I've been the chair of the International Union of Crystallography Committee for the maintenance of the CIF standard for over a decade. So I've got a good idea of how the sausages are made, as we say, in terms of trying to maintain data standards, build data standards, get enough people contributing to data standards. The other aspect of the way CIF works is it essentially describes a relational model. It's describing how the data and the data files can be distributed amongst a bunch of tables. And so my natural bias is to see data in terms of tables, which is perhaps a little bit, which I think tends to be quite powerful and underestimated. I just put that out there so you know what I'm thinking. So the next slide, please. All right, so we've already heard a little bit about CIF. It's been around since 1993, which is before XML for sure, and before OWL and RDF and all those sorts of things. It was designed in order to transfer and archive crystallographic results. And the point about that perspective is that we're only moving things around that are news, are interesting, are different, something that someone doesn't know. So of course, all of the work in ontologies is capturing knowledge that from the point of view of CIF, we assume the person receiving the data already knows. And CIF has caught on very well. There would be over 1 million CIF files around, each of them representing a single structure, whether that's macromolecular or inorganic or small molecule. And we have what we call an ontology, but of course, in terms of axiomatic ontologies, it's very simple. All we're doing is every data value in a file is associated with the data name, and then we go to something, a machine readable dictionary, where attributes are attached to those data names as a way of defining them. That's things like units, a human readable description, and where they're located in a relational schema. And I say there that there are over 10,000 defined. Most of those are for macromolecular crystallography. And if we focus in on inorganic work, then we would be back to about 2,000, including things like magnetism and composite incommensurate structures. All right, next slide, please. Yes, so we've all heard about MO just now, so I don't really need to say anything more about that. So let's skip to the next one. I quite like this slide because it puts all the different things that we mean when we say ontology into a bit of a context. So we can go from a glossary, which we saw in the introductory comments there on the left, right across to the axiomatic theories like MO at the other end. And something like CIF is located in the DB00 scheme position, where we're actually talking about explaining in our machine readable ontology how data values are arranged into a relational schema, which is, from my point of view, the minimum that a software programmer needs to know in order to do something sensible with the data. So anywhere to the left of the DB marker, there's not enough information available for scientific work. All right, so let's go to the next one. The next slide. And so you've heard, you've seen some great pictures from Emanuele showing some of the results of the discussions that we've had. We've been talking about this now a couple of times every month since February 2021. We did have a break for would have been half a year or maybe even a year. And as a disparate group, we've got crystallographers, we've got material scientists, we've got the MO ontologists, including Emanuele, and we have very long and intricate discussions over these meetings. And I've put a list of some of the sort of questions that we're tackling, some of which we've managed to solve, I think, but the answers don't seem to be obvious, but there are answers. I think what Emanuele showed in some of his slides there are things that we discussed only a couple of weeks ago, and I'm now feeling much more like I get what's going on. And of course, you're all welcome to follow the excitement at that URL that I've put at the bottom, and there you can see you'll be able to work out who is actually in the group that's doing this. All right, let's go to the next one. So one of the things that we managed to get done early on is because our CIF dictionaries are machine readable, we can process them into into a form that things like Protege, into an OWL format, and actually get them into an MO representation. But what all of this actually is at the moment is it's just essentially saying this is crystallographic terminology. As I understand what we've done, we've essentially populated the MO ontology with a whole list of terminology, which we can now then link to particular data values in CIF files. And our next step is going to be actually linking these concepts into the other parts into other perspectives. So in effect, our next step is to describe that semiotic process. All right, so getting to the end here, lessons learned from my point of view. One of the great things, it sounds simple, but it makes a huge difference to unblocking conversations, is don't try and define a concept. Instead, describe the concept you're interested in and give some names, because everyone has a different idea of what a crystal is. And if you go and try and define what a crystal is, you're going to have unhappy people. So what you do instead is you define one of those types of crystals and say, you could call this a crystal, or you could call it, and give a list of things it could be called. And that has been a great way to unblock conversations. So that's important lesson learned. And the next slide, which I think might be the last one. Yes, it is. Just a few comments I'll make in closing is, as you've probably picked up, there does seem to be quite a large impedance mismatch between the way the ontology wants us to analyze the world and the way that we normally look at it. And of course, part of that is because the semiotic process is something that we do without thinking about it. I understand that. And of course, it's simply the need to learn a whole new way of expressing yourself. And I've already made that second point earlier on. And the last one is an observation I bring from the relational view of the world, which you can often boil down to saying that this particular value is a function of these other values. And so you're identifying a functional relationship. And it would seem to me that semantic ontologies need to be able to must be expressing these relationships or make it possible to rederive them. So I'll leave it there with those thoughts, and back to the chair.
Thank you very much. Thank you. And I'll hand over to Patrick Lambrix, and again, keep it to a few minutes.
Okay, thanks. So I'll talk about semantic access to materials databases using materials design ontology.
How can you assist in knowing how to change slide? Oh, okay. Was it on the laptop?
Well, I always just use these ones. No.
Yeah, so motivation is that there exist many materials databases, well, which can be about the same topic, but when you query them, you may get different results. So for instance, when we query materials project, OQMD and Nomad for gallium nitride, you will actually get different fields in the results. Also different terminology is used, the formula and composition for essentially the same thing, but even formula is used both for the reduced formula and formula. So if you want to deal with these terminology issues and want to deal with querying multiple databases, you're going to need semantic and integrated access. Another thing that we observed was that These are quite reasonable questions that you want to ask to materials databases. But the questions in red, even though the data that you need to answer these queries is actually in the databases, using the APIs of the current databases, you can actually not ask or answer these questions. So a first step to create a semantic integrated access is something that is Optimate is doing. Optimate is a consortium containing the main materials computational databases. And they're designing a common API so that at least the way that you query the databases it can be the same. What they don't have yet is the semantic part. And this is where we try to help. And we're going to use ontologies to have this semantic and integrated access. So we propose a framework for this semantic integrated access, where the idea is that a user will be able to ask questions to a query answering system. This query answering system is going to reach out to the underlying databases, get the needed data, integrate the data, and present a uniform answer to the end users. And to be able to do that, at development time, we're going to need to create an ontology, which we connect to this query answering system, as well as semantic mappings between this ontology and the underlying databases. And we created a prototype for this, where we have used GraphQL, one of the newer languages, to represent data. So the query answering system is a GraphQL server. We have developed an ontology, which we'll talk about in a minute, materials design ontology, and we created semantic mappings between this ontology and several databases. Now, the nice thing about this approach is that my current postdoc, former PhD student, actually created a system where as input, you give the ontology and the semantic mappings, and as output, you actually get this GraphQL server. So you don't actually need to create the server, you need to create the ontologies and the mappings, and you get the server for free. And we have a prototype of evaluation where we used data from materials project, OQMD. We created semantic mappings based on our ontology. We compared with existing systems. And we showed that using this approach, you could actually answer the queries that we were interested in, while the other approaches couldn't do that. And regarding query execution time, we're quite similar to the existing approaches. So the ontology that we created is called materials design ontology. It's based both on the schemas from the databases that are connected to Optimate, but also using competency questions. These are just a few of them. And we came up with this, where we have a core part, which talks about calculation, properties, structures of materials. We have a part that fleshes out the structure of materials, a part that talks about different calculation methods, and the gray part talks about provenance for data. I visualize this, but underlaying that are actually description logic statements. So for instance, the first three statements say that calculated properties and physical properties are properties, but we cannot be a calculated property and a physical property at the same time. So what we're doing at the moment is looking at, can we extend MDO to cover more of the databases? And we're doing that using a framework that can use textual information. It's a phrase-based topic model approach, where the input is unstructured text, for instance, research articles. It generates frequent phrases, so phrases that occur often in this text. It also creates models, and models are phrases that often occur together in the text. And then a domain expert can use these to define concepts and relationships. Now, this is not always so simple, so we actually created a tool for that. And here is an experiment that we did. So we used articles from 2 journals, where we used the current concept of the materials design ontology as search term. We retrieved the abstracts and the titles of these articles. We put this into a system called TopMine, and then we got 131 frequent phrases and 10 topics. And this can look like this, but this is a list of the phrases that often occurred in this article. And there were also topics, so these are phrases that often occur together and may mean something as a more general topic. And this would lead then to suggested for 80 concepts, and the domain expert is looking at those now to see whether they're interesting for MDO. So we created a tool to help us. For instance, here we have the phrase list. We can click on a phrase and then use this phrase as is, or we create a variant of it to create a concept in our ontology. I'm not going through all the functionality, of course. Here is a topic. So these phrases often occur together. So you can take the whole topic, or you can just click on some of the phrases and create a subtopic, label this, and use that to create a concept in your ontology. And you can also create isl relations axioms for your ontology. So for instance, I've clicked on this phrase, it appears over there. And then I can use another concept in ontology to create an isl relation. So for instance, linearized augmented plane wave method is a density function. So I've shown you a framework, an ontology, and the tool. Thank you. Thank you. We are continuing with the contribution from David Albert.
Great, thank you, Gerhard. Thanks to our projector saviors. So I'm David Albert, and I'm here to speak a little bit about MARTA, the Materials Research Data Alliance, which formed in the US, but now has membership all over the world and quite a bit of activity from Europe. We're sort of a focused RDA for materials, and we're a little bit lighter weight than the RDA. We work, I think, in smaller working groups trying to get a variety of things done. Most recently, we have some funding from the National Science Foundation in the US to make a fair open science research coordination network, which has moved things more quickly. We, of course, work within the framework in the US of the Materials Genome Initiative. I'm going to move quickly through a lot of this stuff. So we work with mostly working groups, and I was trying to think of some that would link directly to people concerned about semantics. In particular, we have a paper coming out, it's in proof now in MRS Bulletin, about how to actually implement FAIR in material sciences with a number of people on it. So you can look for that in a week or two, we hope. We have a working group on data dictionaries that's been pretty interesting. One on MDI provider integration and interoperability, which may be winding down, that Zach Trout, who's I'm sure online, has been one of the leaders of that and running hackathon type activities. One that I think really relates directly to the topics here is a very active group on metadata extractors, and it was great that Optimade was just mentioned because Matthew Evans and Peter Krause and I lead that group, but really Matthew and Peter do the heavy lifting there. And it grew out of discussions in our own MARTA meetings at RDA in 2022, as well as the Matices meetings, which Matthew helped coordinate. I just wanted to give you a quick flavor for how these types of things work in the data dictionaries. June Lau from NIST is at the meeting here, so you can run into June. You may know some of these other people, and there are, we haven't unified our GitHub presence, unfortunately, because we're pretty organic, but you can find the data dictionaries working group on GitHub with some notes, and certainly contact Donnie to get involved with that if you're interested. And as well, we do have a GitHub with the organization named MARTA-Alliance, where you'll find most of the working groups that might be of interest. And so here's the one on hackathon formats. And here's the metadata extractors group. So I would recommend taking a look at this, and the concept really grew out of many of us are writing metadata extractors to extract things from instrument files and headers and the like all over the world. And we thought, can't we share that information at least so we don't all have to redo the same work every time we buy a new diffractometer or a new electron microscope or something that we reverse engineer that from. And so this has been, I think, really useful as thinking of it like an interoperability layer. There are some very large projects that Nomad, is an example that are very advanced in this area and sort of already boiled in what they do, but many of us are much smaller projects as well. And so we've created an extractor schema and a registry, and this says screenshot because it's a screenshot. But there we go, high quality slides we present. But so there are sort of 3 sub repositories. And I think a thing that's really interesting is that we're using LinkML, so we can translate LinkML instances data into OWL. So I think that this is a good place that we can connect. And it's a very active group largely because Matthew and Peter every other week have office hours online. So you can zoom in and people can really talk, focus the issues a little bit and code together to sort of keep things motivated. When you have a dispersed group of volunteers really doing the work, it's a great way to get things actually done. And their GitHub gives us a discussion board as well. So this is one that I would encourage you to look for. This is sort of what we've created, a lightweight metadata schema for extractors, and then a common API specification, not exactly done, for executing extractor code, which is a very similar concept to what's happened in Optimate, and a searchable registry of extractors and file types so that people can exchange these things. And so all of these exist at some level at this point in time. And then the last thing I'll mention quickly is this new initiative within MARTA called Martian, Materials Research Coordination Network. Ben Blazek from Chicago gets the quality name credit there for Martian. We like it, and we get, oh, somewhere there's a little logo of a Martian as well, which we like. And this is an institute among a number of different organizations and folks who've been heavily involved in MARTA. And we have sort of these 4 tracks, one on data, one on making fair models and workflows, one on getting that impact out, and one on workforce development training. But I wanted to mention this one also because Una has already mentioned, and I think we'll hear from about electron microscopy vocabularies. So we have already in our fair data theme, we prioritized electron microscopy. It's something that's so universal across material science, and we've already had a couple of virtual seminars and have 2 working groups spinning up, one on LIMS, but one on microscopy with some identified chairs. Mitra Taheri, who happens to be at Hopkins as well. That's a coincidence, not necessarily related to my involvement. And a couple of others sort of trying to consolidate a couple of work done by a couple of different working groups that happened in the US through the years, one through NIST, one through SHIMAD at Northwestern and the like. And so we're trying to unify that, and it would be really smart for us to connect with other efforts worldwide, obviously. And I think that's what I had to say.
That was a very nice introduction.
We planned that well.
I saw June directly before this meeting, and I like cornered her in the corridor and said, I want to talk to you because I knew this paper. Yes, electron microscopy. And this is something that I'm doing together with my colleague, Volker Hoffman, in the framework of the Helmholtz metadata collaboration. And okay, for those of you who don't already know, Helmholtz metadata collaboration works across the Helmholtz Association. It's the largest research association in Germany, 18 centers, more than 40,000 employees. And we work across scientific boundaries to support efficient metadata handling. And like this, we have close collaboration with NFDI and other initiatives. And the first thing you know, if you know about metadata, is that it doesn't really adhere to these tight geographical or institutional boundaries. So we need to go a bit beyond. And in terms of the electron microscopy glossary, we started this in October 2021. Actually, we spent 1 year mobilizing the community before this, before we launched into active development. We spent a long time thinking about workflows to try and get people on board, because this is quite low level. We work really directly with the scientists. We have scientists from over 22 institutions in Germany, Switzerland, Austria, who are working with us, and we're always trying to extend this. It's slow. So in 1 year, we managed to define 21 terms, and we have meetings twice a month. One developer meeting and one with a plenary talk, so that we get this information exchange between the different initiatives as well. So if anyone's interested in coming and talking, let me know and you'll be very welcome. And we're continuing and trying to scale all the time. In terms of the semantic realm, this is really about this interoperability layer, which was mentioned. When we were talking to the scientists, we realized that there was problems in many places, but that electron microscopy was kind of a glue technology that connected many things in material science and really didn't have a lot of semantics there already. So like many others, we did a text mining approach to try and identify priority terms. We brought these into the community, and we have the scientists telling us what they think is useful or not, because our meetings are directly with the scientists, and we try and helps them in crafting good definitions. And then we also connect all to existing schemas and ontologies. These are primarily the MDMC and Nexus, but we do a lot of Googling to find whatever else is out there, and also try and connect to software, because our goal is to try and bring this to the vendors afterwards. And we've already been in contact with some vendors, and they can't say, no, we don't want to give you good metadata. We want our closed file format because you need to give us something. We say, here's the vocabulary you need, now please implement it first. And yeah, so really this glue technology that links the vendors, the other infrastructures that we're working with, the simulation tools and ELNs together, and having this be some interoperability glue between all of our different application cases. And yeah, very happy to get in touch.
Yes. Glad you worked out that you existed in the slides.
I think that was.
Hi, yes, my name's Stuart Chalk, and I'm going to be talking about something a bit broader in scope and a bit higher level, I guess, and not down so much in the weeds relative to materials. This is an ongoing work. It's a terminology, so it's not an ontology. But I left this reference to a meeting that happened last year with NFDI for Chem on ontologies, because while this is currently a terminology, we certainly are looking towards eventually it becoming an ontology. But as you will see, we have a few steps to go through yet to get there. I am the technical editor for the IUPAC Goldbook, which is where this terminology exists right now. But it actually derives out of a work that IUPAC has done over the last 50 years in terms of defining concepts in chemistry. So, wrong way. So just this is a very, very quick one slide overview. I'll get into some details in a second. So we have a website, goldbook.iupac.com.org, sorry. And at that site, we have currently almost 7,000 concepts defined in chemistry, each one of which has a DOI. There's an API also for the site. We have references in each of the terms to the original source of those terms, which are what are called pure and applied chemistry recommendations, the sort of formal publications of these definitions, and therefore the source documents for them. Going backwards again. There we go. We want to move towards something obviously a bit more semantic in the future. And we are, as you can tell, kind of already talking to NFDI for Chem relative to this. And they've, in that workshop, given us some really good feedback of things that we need to do. I'm going to go through this relatively quickly because we are running short of time here. We really have a lot to do, and you'll see how that is in a second. So here's Pure and Applied Chemistry, a screenshot of the actual journal. Every year, there are one or more recommendations published formally through the IUPAC process. And that's, again, where we get the source of the definitions. The trouble with this now is that over 50 years, there's almost 200 of these recommendations. And having gone through all of that content, almost, I can tell you there's over 23,000 definitions. Some of them, thankfully, are duplicates. I mean that in the sense that, for instance, the Glossary of Physical Organic Chemistry is now in its 4th edition, just came out last year. So there are nominally many terms in that have potentially 4 different versions over time. So if I estimate where we are with that and sort of deduplicate the number of terms, it's probably still going to be in the range of more like 15,000 concepts in chemistry. So we have a lot of work to do. There's not a lot of us involved in this project, so keep that in mind. Here's just an example of one of the definitions. What I'm doing with this slide is one to point out, how we currently, the guidelines that we have, how we currently put together a definition and related information. This is not yet in some kind of, as I said, an ontology. It's not represented in, for instance, SCOS or anything like that yet. But the good thing is, in a very general sense, it's sort of aligned with that idea. So We're hopeful that this is not going to be quite as painful as it could be, but of course, we still have to go through the process. So again, this is where we are. This website that we have right now is something that was developed and put up in 2019. It replaced the previous, sadly, well, actually XML website, but sadly 10,000 static HTML document website, which was not fun to deal with, I can tell you. As you can see, we have a lot of different terms, as I said, over the different divisions. The good thing is, again, we have DOIs for each of the terms, and go forward here. And so this is what it looks like. We have information about what division it was from, different output formats, some of the history, and if it's an item, for instance, that's a quantity that's measured, or it's a unit, we have indications of that as well in the categorization of the information. We have an API. This is very crude right now. I can say that because I developed it. You know, if you go to this website and you look at the API and you go, wow, this is, well, sort of okay, then, you know, certainly do feedback to me, thoughts and ways in which I can improve this. You know, obviously I'm working on this on a relatively frequent basis. What we're currently going through right now is the big task of going through all of the recommendations that we have, aggregating the content from those with all the definitions in them. And thankfully, the publisher of Pure and Applied Chemistry, which is De Gruyter, has sent me, thankfully, XML documents that have a lot of this content in. So I can do some automated scripting to be able to pull the data out. But we built this interface called the term review system, which is literally to take in the content, make sure we have it digitally correct, and then have the individual divisions of our UPAC go through and verify these terms, make sure they're accurately represented, and then do any minor typo cosmetic updates that are appropriate so that we don't change the definitions, because that's kind of like the formal UPAC process. In terms of digitizing this, we cannot formally change the definitions because they need to be the same as what is in the original PAC recommendations, and those have legal significance for a number of different reasons. Come on. Doesn't like me. Timeline, I'm optimistic. Maybe others aren't, but I'm optimistic that maybe by the end of next year, we can get all this data in. Now, I know that's a long time frame on today's sort of agile development lifecycle, but we are a volunteer organization. I am a volunteer. I don't get paid to do this. So obviously, if there's anybody out there who wants to help, please let me know. But we have a lot of stuff to work on. The Orange Book, Analytical Chemistry, is the one we're working on right now, which has been revised, thankfully, in the last few years. And we've just got the official publication of that set of terminology across the area of analytical chemistry. That's formally out, but we need to get all those terms up into the Gold Book, so obviously people can use them. So there's a lot of work to be done here. Here's the projects. I'll skip over that for the next second. And here's contact information if you want to get in contact with me or others that are involved in the project. Thank you.
On to our next presentation, which is going to be given online by Philip Format.
Yeah, thank you for giving me the opportunity to present here today very briefly what we're doing in NFTI for Chem in the task area called Terminology Service. NFTI for Chem, for those of you who don't know, is one of the many consortia that make up the large-scale national research data infrastructure project called NFTI, which is initiated and funded by the German Research Foundation. Next slide, please. The most important aspect of our terminology service is to build up a registry with which our stakeholders can find, access, understand, and use the ontologies deemed relevant for research data management. And we decided to reuse the code base of ABI's ontology lookup service for our TIB general backend. And we have added to it the concept of collections to allow the curation of the indexed ontologies into domain-specific sets, because the reason being that the TIB is also involved in other other NFTI consortia and other projects which have the same need for such a registry. So with these collections, we are then having multiple domain-specific React-based front ends where we can make those collections publicly available. For instance, the NFTI for Chem or NFTI for Ing terminology service only hosts the ontologies relevant for their domain and that are present in these collections. And TIB General Terminology Service is a central hub that contains all the collections and that links to these domain-specific front ends. And also, when we speak about terminologies, I would like to say that we are not only indexing ontologies, but also SCOS vocabularies. Next slide, please. When it comes to the user interface for browsing the terminologies, we are focused on catering to the expectations of users with regard to already existing services and applications. So we provide a common tree view for classes, properties, and individuals, but also started to implement a list view for those who are more interested in understanding ontologies and terminologies as tables. And the trees can be navigated just like you navigate your ontology in Protege with the navigation keys. Besides having these common views of looking and understanding ontologies or terminologies, we also plan to provide overview features with which one can better grasp the import dependencies of ontologies or the alignments and mappings between ontologies. And by integrating the terminology service with platforms like GitHub or GitLab, we hope to be able to assist our users when it comes to requesting new terms in the indexed ontologies, or to get a better overview of open issues in one ontology as well as across multiple related ontologies, in order to understand what the current development status of these ontologies is, and maybe to be able to determine how one can help to improve it, or what one needs to wait for. And of course, such work is always dependent on and limited to the APIs and the metadata that are available. So we are also invested in pushing metadata standards like the MOD ontology or SSS-OM for mappings, as well as using tools like Robot or the Ontology Development Kit in automated workflows. Next slide, please. Now, coming quickly to the NFTI for Chem collection. Ontology collection, I'd like to say that it is based on an overview we did and published in PAC, and where we looked at the currently available chemical ontologies by looking at how fair they are and how far they can be reused in our research data management context, and what kind of gaps or issues there are to be addressed and worked on. And luckily, we can stand on the shoulders of giants, as there are already quite a few well-established chemistry ontologies. But when it comes to their interoperability and with a focus on data integration, we saw that there are still quite some harmonization issues to be resolved. And for this, we held an Ontologies for Chem workshop last September, to which we just heard a reference, and where we brought together maintainers and developers of these ontologies, as well as tool developers, and discussed the issues we identified, current development status of ontologies, and what we can do together in order to make the ontologies that are to be used in a modular fashion to work seamlessly together. You can watch the recordings of this workshop on YouTube, and we are about to plan our next workshop this year, for which we would like to invite you. And if you would like to help us organize it, please feel free to reach out. Next slide, please. As part of our terminology work, since we identified gaps in existing ontologies or other issues, we also contribute to existing ontologies, and just recently started to develop a new ontology, the vibrational spectroscopy ontology WIPSO, in order to address the gaps that are resolving around vibrational spectroscopy and Raman spectroscopy in particular. And for this, we're working together with domain experts from NFTI for Chem affiliated universities, the domain experts from the Charisma project, UPAC, and one from BASF. And this development is being done openly on GitHub as usual, and we have open regular calls about once a month. And yes, we use these meetings and the experience we gather of this endeavor also to improve the terminology service in terms of making feature requests such as the term list view. As we've heard, some people are more used to looking at things in a tabular fashion than in a tree fashion, and this should be possible. This should be able to get domain experts involved who we need in order to define and improve and work on ontologies. Next slide, please. Yes, and also part of our work is to work together in the NFTI project with other NFTI consortia when it comes to the harmonization and mapping of ontologies. There is the section metadata in NFTI, in which there are 3 different related working groups, one for the terminology services in general, one for knowledge graphs, and one for ontology harmonization mapping. And we're involved in this as well in order to discuss with other domain experts and other NFTI consortia the different top-level ontologies they use and how those can be mapped in order to assure interoperability of consortia that are overlapping, such as NFTI for CAM and NFTI for catalysis. And so we are looking at how we can make sure that we can work together seamlessly. Next slide, please. And what has become clear within these working groups that I would like to say here in this talk as well is that I think, or we think, we should be helping to get more documentation out in more centralized places, because it's scattered quite a bit, so that people interested in working at the same things have a chance to understand what we're talking about more easily. And when it comes to harmonization between ontologies, we also identified that it would be great to have a better way of documenting and viewing interdependencies and design patterns of ontologies. So having some common registry for mappings between ontologies and between design patterns and shapes would be a great thing to have for the common practical purpose of doing data integration that is fair at the end of the day. Next slide, please. Yeah, and with this, I'm done. Just wanted to show you here some links that you can follow up and to get in contact with us when it comes to NFTI for CAM. Thank you very much for your attention.
Thanks a lot, and we'll continue with the presentation by Carl.
So where are you?
Yeah. Please, yeah, again, keep it true.
Okay, my name is Kwang Lee. I'm very happy to be here to introduce our effort. So
It's yeah, right.
yeah.
There you go.
Oh, yeah, just
slow.
yeah.
So
It
is.
So since 2020, we launched a national center to handling all the material research data in one place. And one of the mission of this center is to build a kind of standard that can make a homogenized structure of materials data. So I'm in charge of this committee, and our approach to this issue is that totally from the viewpoint of the material researchers. So we want to build a kind of a well-structured materials data that can be directly used for machine learning or data analytics. So that we need to build a well-structured material data so that we have to collect under the same structures and also to be accessed on these structures. Oh, sorry. So we think this is a kind of a lock base of the data-driven materials design ecosystem. And what we want to standardize is, I think this is a kind of a language in this community. So we should build a standard structural material and data. This is a kind of grammar, so that we can understand what this word means in these materials properties. And also we have to clearly define the keyword of the data so that we should use the same keyword of same properties. So these two things should be standardized in our community. So as a product of this community, we try to build a structured data keyword dictionary so that this is also provided in terms of the human readable and also in terms of the machine readable in JSON format, so that any data platform can utilize this dictionary to build their template for data input and also data out. So in this viewpoint, this is kind of, I think this is very similar to ontology concept. But the challenging issue is how to build the structures that can cover a whole wide range of materials. As you can see in these pictures, actually different materials can have very different structures of data. Even we can consider it is a different discipline. So that in order to make a kind of some common structures, we should discuss a lot, very extensively discussed for the last 2 years. And then where is it?
Very slow.
Go.
You're waiting for the Zoom.
I think the next slide is the most important concept of our data structures.
Most complicated slide, maybe too, right?
Yeah. So we decided to introduce a concept of material system. So material system is defined as an object that is composed of one or more materials to characterize the performance of material. So if I explain this concept using these examples, for example, catalytic materials, we want to characterize, the data should be characterized the catalytic properties. But in order to characterize the catalytic properties, we need the supporters and also promoters. So material scientists know that the performance of these materials sometimes dependent on the supporters and promoters. So we have to include all these data in one data set to understand the performance of the materials exactly. So this is the concept of this one. So I'd like to show I think we need a better notebook. Oh yeah, okay. Where is it? Okay, there we go. Oh, okay. So we just follow the materials as we are doing in the laboratory. So it's a catalyst. If one develop the catalyst, it should have information of synthesis information and also intrinsic chemical and physical properties of these materials. And all the properties should have a analysis condition and analysis method as a kind of metadata of the properties. So all these data should be structured like that. And also we have to have information about supporters in the same format and also promoters in the same format. And by assembling of these materials, we can define the catalytic systems. And then this system should have information about performance of the catalyst. And that performance should have information about the test condition and also analysis and characterized method. So all this information should be included in one data set. And we found that this material system concept can be applied in wide range of materials, composite materials, and also electronic materials and the energy materials can be considered in one data system concept. So the next page is coming soon. All right. So in our suggested data structure is there are just 3 groups of data. There's the materials sections, and there is a number of materials information, which is composed of these informations. And then there is a system sections, and the system section have a configuration part. These configuration actually define the role of these materials in these material systems. And then it should have a process technology to assemble this system and also its performance. So by structuring like this, we think that these materials can be used for machine learning to design the new materials from existing data. So what is that? So this is the one example of the standard data structure, standard data structure of material. And our system is that they should have a metadata of this material, explaining this material set, and also end materials information, which is used in this material system, and also system informations like this. This is one example of the systems. Next. And in the vocabulary, we should, in order to define the structures, this vocabulary, there is 5 groups of the vocabularies: metadata vocabulary, materials vocabulary, and system specific vocabulary. And also in the analysis and the material process can be used in common in various materials, in various systems, so that we make a separate group of these informations, this vocabulary informations in common vocabulary for analysis method, and also common vocabulary for material process. And in addition, we also provide a definition of how to express numeric data in this database. So this is the dictionary that we provide, and this dictionary can be used on the structure that we suggested as a material system. Okay. So I think the late part I should skip, but I think these are all the very details about this. Thank you very much.
Presentation, and then we come to the final contribution, which is from
I'll be very brief.
Oh, at the moment it works, so I'll pass it on to you.
My name is Scott McClellan, and I ran a small study of term overlap in the map portal ontologies. We selected 5 ontologies from the overall 20 that were in there at the time. This was done in 2021. And what we were looking at was how term overlap effectively is an element of interoperability. And so we looked at the degree of overlap among these ontologies, and we also looked at the semantic ambiguity. We used the basic tools that were available in Map Portal, which utilized a URI matching and a terminological matching. And what we discovered were that the highest rates of URI matching were largely limited to ontologies developed by Fraunhofer. And these had an identical set of 347 terms that overlapped specifically between these sets of ontologies. The second highest set of URI matches that we saw were directly linked to basic formal ontologies. The terminological matches were a little bit more evenly distributed. You can sort of see here that the loom, which is the algorithm which matches term level on top matches term, gives a better idea of greater frequency and more even distribution. And what we saw then is that possibly the use of these ontologies by a small set of institutions can create a sort of an isolated sort of view of the world, leading to less geographic distribution. Map Portal is much more limited to ontologies that are European based. There are a large number of ontologies that are US based that might also be of use. Over reliance on abstract ontologies might limit view of the world, things like basic formal ontology. And when they undergo version changes, they don't match up, they don't align. So there is actually one ontology that showed an older version of BFO, which shows no URI matches in Map Portal ontologies. Some of the possible solutions, as many people have mentioned, SESOM, which is the ontological mapping setup. At the Metadata Research Center, we've also been utilizing Hive, which links ontologies to a variety of ontologies and can be used for automatic indexing. And we've also been using a crowdsourced tool called YAMS, which allows a community to enter terms into a system and then using a Stack Overflow setup to vote on terms. And we feel that this is a bottom-up level that could help with term overlap.
Thanks again to all our speakers. At least despite all of the hiccups, we managed to get all the talks within the allotted time, and we will, now move over to the discussion. I wanted to talk about the working group and so on, but I mean, just to start, I would say, we'll take 15 minutes. Yeah, those of you that want to leave can leave. Go to another session. Oh yeah, it's because the session was scheduled for 11. Okay. Yeah. So there's the going a little bit into the break, but as I said, we'll have to deal with the things as they are. I think first, before we talk about what's next, I just want to give an opportunity, also check the chat here in terms of questions for any of the speakers, your thoughts both from people online and also here on the room. Please, I want to open the floor for that first. Martin.
I'm wondering, so many definitions of properties. How does this relate to I adopt? Anyone can answer. I mean, this. How does everyone?
I would answer that by saying it absolutely relates to I adopt. I adopt is sort of an implementation of how to represent such things in an ontological sense. So I think it's definitely relevant. But in a sense, it's sort of a separate piece than maybe what this community is really should be maybe more talking about. But is one to disagree with.
Any other thoughts from me? It seems like there's what is great is to see a lot of developments, a lot of people doing stuff. Also in terms of the tooling, I like what I see there. There's in terms of how do we develop glossaries and terminologies that we've seen a number of things here. And now I see the hands going because I also wanted to say, okay, this is great. We need this tooling and approaches, but also we need there to make sure that we develop this into a common resource about how we do that. Yeah.
So I've got to point out there's already a recommendation, an RDA recommendation on a materials vocabulary that was developed in this context. It's used in the NIST Materials Resource Registry. And what I find a little frustrating is that we're not learning from things we already did. We're going off and reinventing without coalescing. And I think we need to come to terms with that, or sort of the whole gist of what we're here at RDA for is to reach consensus and to build virtual standards, if you will, ad hoc standards, community standards that we can all agree to. So I just see a lot of repetition here, which I think is unfortunate.
Where do you see the repetition? I mean, if I may, I mean, the materials vocabulary is a list of 3 tiers of a list of terms, without definition of terms, without conceptualizations of terms. That's not I mean, it's a taxonomy that can be used and has been used effectively. But it's not a resource for ontology because, I mean, I don't know what it means.
Well, okay. Still, I'm seeing, a dozen parallel efforts here that we really ought to somehow coalesce.
Absolutely.
Into
100%.
Yeah, that's I'm sorry, but I don't mean to offend anybody, but I think we need to do better.
Yeah. Jane.
Hi. Okay, thank you. I just want to say thank you, Gerhard, for putting this together. And I'm going to push back on Bob for a second, even though that vocabulary is incredibly I think we're at the state where it's kind of like let a thousand flowers bloom, because each of these projects that people are talking about, even though there's some overlap, they're each bringing something different to the table. And we've got to let these projects move forward and then share. We can build all these tools, but what we all need to be thinking about and sharing is, how do you get the actual, on the ground material scientists actually use these tools, and being able to share our actual demonstrations? How do we get, some of them, we have material scientists working with us to help develop, but are they using them in their workflows? And I don't think we're quite at there yet with success stories. And it just demonstrates where we are in this process. And it's good stuff to see these things happen. So I think we definitely need to work on it.
Yeah.
And this is really exciting.
Thank you for that. Then I had Jan, and then there was also, yeah. Okay.
So just to say, I mean, it's impressive to see all these different initiatives from all over the world in the end, right? So I think one of the crucial aspects is to get to know each other. We discussed to avoid having semantic silos, right? Because we're all building semantics. At some point, if you don't agree on common ways of doing it, then we just create the silos we try to deconstruct with the semantics. And it's good. I agree with James. Good that people are doing this on their way, because building an ontology of material science is a daunting task, right? So you cannot do it on your own. And because people have different perspectives that needs to come in, but we need to make sure that it's interoperable by design, and to reuse the tools that exist. So one of the things is, when you develop an ontology, well, something to do by portal, right? It's there, so use it. It's like based on bioportal now. Bioportal in the biomedical domain contains more than 1,000 ontologies, right? And they are made accessible to machines. People can actually leverage them. I think a group that kind of create that cohesion across the different initiatives.
David, and then no.
So I kind of want to endorse what Jane said very quickly, that we need people to use them, and what Jan said, but we need to think more deeply the way material scientists use it. And it's very different in very different places. I work on a lot of different projects. We have a very versatile data model. And I think one thing that we hear a lot about in vocabularies are all these nouns, definitions of this being made of that, being made of that. To a material scientist, it's all about the verbs. It's about the processes, and we don't capture a lot of that, right? I can take milk, butter, eggs, flour, and I can make a cake, or I can make a cookie. To a material scientist, it's all about those processes, and how we capture those workflows, totally different. Whether you're working on polymers, or you're working on alloys, or you're making single crystals to put thin film deposition on top. And so in my data model, we capture processes, but we do it very atomistically, like one might think of a model, every step, there's an input to a process, there's one output. No one works that way in the lab. So we have to both develop that quickly, and then for applications, I think, abstract pieces of that away, right? So we still capture that, but we have to think about the application and give people tools, usually graphical tools, so that somebody in the lab actually enters things, understands, not enters the manual way, but enters into that pipeline of thinking that way. So I think that we need a lot of different thoughts on that. I've had 6 different students working on 6 different projects. One, people work in a Jupyter notebook, another, we have a graphical editor, and they're all different. And some work, some don't.
Yeah, that's so true. And we only touched on that a little bit, and thanks for bringing that up, because the process is so important to the material.
It's what it is, yeah. And it doesn't in basic presentations, because it's easier to explain things in terms of the nouns. I think it doesn't get shown. So the material scientist doesn't grab onto it.
Yeah.
So I endorse the idea of a working group, but one that moves fast.
Thank you.
Yeah, thanks. So my name is Clément Dampé. I'm a little bit outside of this group and this discussion, but I will necessarily call for discussion with the recent group that was presented yesterday. You guys were in some of you were in the room, so we are working strongly on representation of properties that was mentioned with the IADL, but also on semantic artifact catalogs. And I've seen there, like today presented and cited two semantic artifact catalogs, the NFDI for CAM, but also the MAT portal. The Commons has also released another one with the portal technology called Industry Portal that is being from Init. So there are a lot of activities there. So it's really a call for working together in order to harmonize a little bit that. And I want to mention that in the context of the Fair Impact project, we have a deliverable that's going to be an API, a common API that different semantic artifact catalog, ontology repositories can implement to actually become interoperable with one another. We're going to base that on a standard that was mentioned called MOD that we've done in the action a few years ago. And once we're going to have this standard API and things like the NFDI for CAM and the other NFDI's terminology service, the one that are not necessarily based on the OntoPortal technology, there are going to be a few ones. All of them could implement that API and then talk the same thing. So all of the software that will be based on those terminology server will be able to go from one server to the other ones. That's really part of the action in terms of harmonization we want to do. And the second comment will be I was super excited to discover the term the NFDI for CAM that was presented and because that was the very first use of OLS, which is basically the competition technology for us with the OntoPortal, used in another context than OLS. And I think NFDI, TID, and CAM did a great job on that. Although I'm still thinking that some convergence also can be achieved here with what we do and the context of materials and chemistry and industry. And this is a good context because you guys have those three portals now and you're going to have to discuss one another and things like that. So it's a call really for keeping in touch on those aspects.
Yeah, so important. Thank you for that. And we need exactly not divergence of the tools, but somehow convergence there. Yeah. Sorry, just
to back up what Clément was saying on WISIG. I mean, tons of the things that you discussed today are going to be discussed on WISIG in a general context, meaning across domains. So it's definitely important that we work together.
Yeah, so definitely that's absolutely So we do if we do a working group, we want the working group to focus on that. It's more of utilizing then the outputs and avoiding reinventing that and getting the use cases and the experience of that. Yeah. So over to Samantha.
Currently a question rather than a comment, and maybe we'll have some opinions. But is there a place for a upper level ontology here? Because I mean, I've always thought they sounded very useful from a harmonization perspective, but equally obviously the issues you raise, versions and such like. Would that be useful or would that be more problematic, or could we do it in a better way than the BFO?
Maybe Emanuele wants to answer, but I mean, I of course.
Emanuele left. So what do you mean exactly? Like, is there a place for?
Well, if we're talking, people are trying to do lots of mappings and lots of terms and lots of different initiatives that are coalescing on that. Would we want? Is there a place for one?
I mean, I would say yes. In my view, I mean, it's a good. Yeah, there's also raised hand from Jesper. I will let him speak in a minute too. You know, I mean, for example, when I was looking at what Riol presented here, you know, you can put these into, you know, map them very well. These metadata into the MO generic concept. So, and I think that was the purpose of creating MO. It thought, you know, quite hard and deep about very generic concepts that work in applied science context, and therefore, you know, that should help with integration. But we will have to test that out in the end and the practice. Sorry. Yes, but can you speak?
I will try.
Yeah.
I think the importance with top-level ontology is both that it provides a very good logical foundation. So you have a good theoretical background, makes things consistent. But even more important, if we want to do anything cross-domain and ensure exchange of data between domains, then we need more generic concept at a higher level, and there also the top level ontologies are very important.
I think there was also a question here which is kind of related to that. Are these from Philip online, if you want to speak to that, are these vocabularies in the schema mapped to existing ontology terms, or is that such a mapping planned? Maybe Philip, if you want to also add to that, was it just for a particular talk or?
Yes, this was a question regarding the Korean metadata schema, but related to what was just been said in the NFDI harmonization and mapping working group, it became clear with regard to the interdependencies between domains that we will not be able to agree upon a certain top level ontology. So we should be able to deal with the fact that certain communities rather want to use BFO, other communities would like or need to use AMO, whilst others use Dolce or whatever. So for us, I think it's more important to focus on the fact that if we have good tooling that can help in the pragmatic integration by having mappings and mapping registries, then we are fine and we can work with those different needs. So that's what we should focus on. And I think it would be more pragmatic than to waste a lot of time discussing which top level ontology and which philosophical concept is more adept for all. This will just not work because language is not that way.
Yeah, just one comment on that from the OntoCommons project has exactly worked on that, or maybe Jan wanted to say the same thing, at least between Dolce, MO and BFO, to provide what we call a top reference with mappings that already are elaborated so that you can go more easily between one and the other, exactly to try and overcome that issue to some extent. But I said we'll go until 22, which we've already gone over, and I would like to thank everyone again for participating. Sorry for the problems. People online, and you're happy to if anyone wants to join in here, or we'll probably have some more discussion. Thank you.
Absolutely.